Hello and welcome to the wolfSSL live webinar, wolfSSL and Weston Embedded Interoperability Partners in the IoT Space, presented by wolfSSL Senior Software Developer Anthony Hu and Weston Embedded President and Co-founder Janos Magasrevy and Network Stack Lead and Co-founder Yanko Sosa. My name is Shizuka and I'll be moderating the webinar. All attendees will be in listen-only mode. If you have a question, please use the Q&A box. We will host a Q&A session following the presentation. The webinar will also be recorded and made available on YouTube channel shortly after the presentation. If you'd like to stay updated with all the latest from wolfSSL and Weston Embedded, follow us on X, connected with us on LinkedIn, and subscribe to our YouTube channel. Also, feel free to email us at wolfssl.com if you have any additional questions. Now, let's take a quick look at today's agenda. We start with a brief introduction to wolfSSL, followed by an introduction to Weston Embedded. Next, we'll dive into an overview of our wolfMQTT product, and then give you an introduction to CSNet. Then it'll be time for a live demo, where you get to see everything in action. And finally, we'll wrap up with a Q&A session where you can ask any question you might have. And now I'd like to give a brief company overview before we move to the technical presentation. Today, wolfSSL secure over 5 billion connections. We have more than 2,700 OEM customers and dozens of resellers. wolfSSL consists of over 50 dedicated employees, most of which are engineers. This progress is, of course, supported by a strong partner network that we are proud of. Since the beginning, our engineering team has developed several embedded security products, including wolfCrypt with DO178 support, FIPS certification, and a FIPS-ready offering, MQTT up to the V5 specification, SSH-v2, TPM 2.0, a secure bootloader known as wolfboot, Java wrappers, and JSSE support, commercial support for Coral, and our latest product offering, wolfHSM. These offerings are accompanied by strong maintenance and support plans up to the 24/7 level. We also offer full service consulting. And now I'd like to turn it over to Anthony, Janos, and Yanko to discuss wolfSSL and Weston Embedded Interoperability Partners in the IoT space.
All right, so thank you for joining us in this partner webinar. I'm Janos Magasrevy, and I'm the president and co-founder of Weston Embedded Solutions. We specialize in embedded software, focusing on real-time operating systems and communication stacks. Let me give you a brief overview of our origins here. In 1992, Jean Labrosse, who's a well-known figure in the embedded software industry, created the first version of the highly popular MicroCOS real-time operating system. It was in 1999 that he decided to launch his own venture, offering customers a commercially licensed real-time operating system. This led to the founding of Micrium Inc. Over the years, Micrium expanded its product portfolio beyond just the kernel, adding a TCP/IP stack, a file system, a USB device, and a host stack, among others. In 2016, Silicon Labs expressed interest in the company and decided to acquire it. However, in 2020, they made the decision to divest Micrium. After the announcement of Micrium's closure, we as Micrium engineers since the early 2010s collectively decided to start Weston Embedded Solutions, with the mission of continuing the Micrium legacy of clean, reliable, and trusted embedded software. To talk more about the evolution of the software, let's go over the following diagram. As I previously mentioned, MicroCOS was released in 1992. With Micrium's foundation came MicroCOS 2, the second iteration of MicroCOS and well-known real-time kernel, even used by NASA on their Mars Curiosity rover. In 2008, MicroCOS 3 was released. It was designed to improve but not to replace MicroCOS 2. Then Silicon Labs acquired Micrium and they made modifications to tailor MicroCOS 3 to their specific hardware. They call this Micrium OS, and it's available today through their Gecko SDK. In 2020, the Micrium Micro-C product line was made open source by Silicon Labs just prior to closing Micrium. This code is available on GitHub. After that, we decided to create our own commercial fork of the Micrium Micro-C products, and we called it Cesium RTOS. Today, every Micrium Micro-C product has been enhanced with new features and bug fixes in our own commercial brand, Cesium RTOS. Cesium RTOS is indeed the next generation of Micrium's Micro-C OS software. Here's a high-level view of our Cesium RTOS. It offers two real-time kernels. They are CSOS2 and CSOS3. Both of them have been widely ported to a large number of semiconductor manufacturers. Our communication stacks include CSNet, which we will be covering later on in this webinar, a USB device, and a USB host stack. Finally, we also offer a FAT file system called CSFS with support for popular storage media such as NOR, NAND, SD card, RAM disk, etc. For those of you that are interested, we have a 30-day free evaluation of our Cesium RTOS with full source available, example projects, documentation. Just go to our website and request it from there. Here's where you can reach to us directly. You can visit weston-embedded.com. You can send us an email to sales@weston-embedded.com, or simply give us a call to 954-655-2048. We are located in Weston, Florida on the US Eastern Time Zone. Here are some of our partners and distributors. Obviously, we have wolfSSL, embedded office in Germany, who's been a long-time partner since the Micrium days. We are the only authorized seller of their flexible safety RTOS in North America. So if you're in the need for a pre-certified RTOS, don't hesitate to contact us. We are also part of the partner programs for NXP, ST, Xilinx, and IR. For our distributors, we have BMR in China, Ruby Embedded Technologies in India, SiteSys in Israel, SwiftAct in Egypt. Since our last webinar, we've added a couple more distributors. In Japan and Korea, we have DIOIZ, and for the South Pacific, we have Testec. Percepio is our newest partner. We recently launched integrations with their tracealyzer tool and our kernels, which allows the user to have a graphical view of the runtime behavior of their system. And now I'll hand it over to Anthony.
Thanks, Janos. Hi, my name's Anthony Hu. I've been with wolfSSL for about 4 years now. I've been in consumer electronics for almost 25 years, a software developer in the consumer electronics industry for about 25 years now. And I'm here to tell you a little about wolfMQTT, and then we'll show a live demo afterwards. So yeah, wolfMQTT is obviously an MQTT's library that supports MQTT version 3.1.1 as well as version 5.0 of the protocol. We also support the MQTT sensor network at version 1.2. So if you're looking for stuff on Zigbee as well as UDP under the hood, then we can help you with that. Importantly, wolfMQTT uses wolfSSL underneath it for the TLS layer. So if you're using secure MQTT, then you'll be able to use all the goodness within wolfSSL as well. All right, and now we hand it off to Yanko Sosa, who is a member of the Weston Embedded team.
Thank you, Anthony. Hi, I'm Yanko Sosa, and I'm the Network Stack Lead and co-founder here at Weston Embedded Solutions. Today, I'm going to talk about our CSNet network stack and its MQTT client module. CSNet is our TCP/IP stack that runs in conjunction with our CSOS2 and OS3 kernels. It supports multiple interfaces and multiple IP addresses per interface, also known as multi-homing. It supports both IPv4 and IPv6. independently or concurrently. We have a BSD socket API supporting the most popular socket options, featuring a POSIX-like error handling. It is also designed to be scalable, and it contains only what features you want. And if you want to minimize your footprint, it's possible to turn them off. And of course, we have an SSL or TLS, as it's called these days, TLS socket option. So this is an overview of the features that we support. We have a wide array of processors that we support out there, anywhere from NXP, ST Micro, and so on. We have support for DHCP with our DHCP client on IPv4. We have a DNS client. We support HTTP, FTP, and MQTT, which is the topic that we're addressing today. FTP, TFTP, SMTP, and SMTP, and a telnet server. So this is what we call our network applications. Real-time kernel is required, and CSOS2 and CSOS3 work out of the box, and that's what we recommend. We have TCP and UDP support on our transport, and we have MLD, ICMPv6, ARP, of course, and all the other underlying protocols. We support Ethernet, Wi-Fi, and loopback. And we have two sets of socket APIs. Like I said before, we have BSD API, and we have our own proprietary API. Recently, we added support for raw sockets, which is a feature that we're very excited about. It allows applications to bypass the transport layer and communicate with the network layer or data link layer directly. And that basically allows us to interface with other protocols that we don't currently support. But if you have another stack, let's just say like an Ethernet IP or EtherCAT stack, you can communicate with it using raw sockets. And on the right, we have a list here of the RFCs that we support. So this is how CSNet is organized. We have the network applications interfacing what we call the TCP/IP core, which has all the underlying protocols of the stack. The core itself communicates with an SSL stack like wolfSSL through the secure port that we developed. We made it a priority here to keep CSNet modular, just like its predecessor, MicroC TCP/IP. We offer the same API and network applications as we did before, but we have more features. We have continued development and active maintenance. Since 2020, CSNet has seen over 10 releases that have corrected bugs, addressed serious vulnerabilities found both in-house and reported by cybersecurity agencies. We've also added new features like diagonal support, like we said before. And we also added an option to use the new Reno algorithm for improved recovery after congestion events subside in network environments with long round trip times. And this benefits those applications that communicate over the internet over large geographical distances. So this is an overview of how we integrated wolfSSL within CSNet. We implemented an internal task that acts as a gatekeeper to manage access to the wolfSSL library. Our network applications shown here in the star diagram on the left, for example, HTTP or MQTT, they interface with this task, and then the task synchronizes access to the wolfSSL library. So if you want to connect, receive, send, accept, those are the common socket APIs. It'll call these secure counterparts using the internal task. This also includes your custom application. So if you want to do basic things without using our network apps, it goes through the internal task as well. So the way this works is through the APIs, you eventually reach the NetSecure API here. It's in the middle of the diagram on the right. And then we wait for the result of the operation, sending the plain text data and then waiting for the encrypted data to return. And then the IO callbacks are called to perform the IO operations, and that's how eventually the data makes it into the wire after going through the driver. So the details of initializing CSNet is outside the scope of this webinar. We usually tell our customers to start off with one of our example projects. As Janos mentioned, we have several example projects on our website, which would have a BSP and an Ethernet driver already implemented for a particular evaluation board or MCU. With that said, these are here on this table, the configuration parameters in CSNet that are relevant to security as it pertains to wolfSSL. On the left, we have the definitions as they appear in our configuration file, netconfig.h. And then on the right is the effect that it'll have on wolfSSL. So we have a user settings.h file that responds to whatever changes you make to netconfig.h. So the advantage of this configuration scheme is that it reduces the guesswork of determining which wolfSSL features will be supported by the underlying network stack. We start off with that user settings.h, which is the default that gets published by wolfSSL, and then the changes, you can make changes as a user, add more memory, and so on if you need to. But there's a couple of whatever's here in bold is what gets affected if you change it in netconfig.h. So securing a socket with CSNet. If anyone is familiar with BSD socket programming, it's pretty much the same thing. This is an example here with our BSD version. It just basically you would have to open the socket, it'll give you the descriptor, and then at a minimum, we need to call these two APIs to number one here with netsock config secure. We would have to secure the socket. This is how the stack knows the data is to be encrypted eventually, and to contact the wolfSSL internal task to carry out the operation. And then NetSecure CA cert installs the certificate in the format that you specify. We support PEM and we support DER formatted certificates as an input here. Okay, so let's talk about our MQTT offering. We support version 3.1 and 3.1.1. We support quality of service levels from 0 to 2 for published messages. We can connect with multiple brokers at once. And thanks to wolfSSL, we support mutual authentication for the client and have support for the ALPN and SNI TLS extensions, which are important when you're trying to communicate with the broker. If the broker, for example, AWS requires you to use a very specific ALPN value or string, and if you don't put it as they specify, it'll reject the connection. So it's very important that we have that feature, and wolfSSL has it. And of course, it also has its own internal task with callback functionality. So whenever you connect, whenever you get a disconnection event, or any event for that matter, you get a callback executed, and then you can either log that or perform some activity as a result. Right, so this is configuring MQTT client. So this is a typical setup, and this is an actual screenshot of the example that we're going to run today. Some parts are abridged, so it will fit on the screen. But essentially, we have to set a few parameters on an MQTT connection object. So starting out with the broker name, the port number that you're trying to reach. So typically for MQTT over TLS is 8883. A client ID if it's required, What else? The keep alive, the timeout of the connection, an inactivity timeout, and then a series of callback function pointers that you set up here. And then that basically tells the MQTT client what to execute, which function to execute in terms of whenever you get a completion or a connection event, an error, a publish acknowledgement, subscriber acknowledgement, etc. So how do we configure ALPN? We have an ALPN configuration data type that takes in a string and an option for wolfSSL in this case. And then we also have a mutual authentication configuration structure that allows you as a user to input the client certificate issued by the server, by the broker, to identify you as a client and accept the TLS handshake. So during the handshake, it'll ask you for this information, and wolfSSL provides it. You have to pass in also the private key, and then you specify what format it's on, if it belongs to a certificate chain, etc. So all this information is recorded here, and then we pass it along as in the secure configuration structure that we at the end there set the parameter for, right? Notice here there is a trust callback as well. This is part of the CSNet functionality. And if for whatever reason the handshake doesn't get established, we execute this callback and give you an error, and then you can debug that error however you want to. Right, so this is kind of like the lifetime of an MQTT message, right? So what do we do with our MQTT client? How do we initialize it? Well, we got to start out with an application task that calls MQTT client init. And then after that, as we saw in the previous slide, you set the connection parameters, and then you open the connection. So after opening the connection, it gives you a socket ID it automatically, and then it performs the handshake as well. So once that's done, you perform an MQTT client connect, and that sends an actual connect message, an MQTT connect message to the broker. Then you can also subscribe to a topic, publish, unsubscribe, disconnect, etc. So this is not the entire list of APIs, but you see here in bold the two APIs that are going to be showcased later on in the demo. And then this message gets passed along to the MQTT task, which processes it, and it executes the callback functions that I mentioned before. As part of the processing, of course, is sending the plain text data along to the CSNet core, which then copies it into a buffer. It prepares the socket for encryption, and then passes that to the wolfSSL internal tasks through a command queue. And then the wolfSSL task performs the encryption and so on, and returns the encrypted data, which the CSNet core receives it and puts it on the wire. So that's basically how it goes from your application to the wire.
Okay, so I guess I'm going to be taking over from here. Thank you so much, Yanko, for all those amazing details. We're going to be a little bit simpler on the wolfSSL and MQTT side. And that's just because with Yanko solution, it's an embedded solution. So there are lots of details that can only be shown in code. Whereas for us, we're just going to kind of gloss over the code and let you kind of investigate that on your own. But we will give instructions on how to build and configure all of our software. So just about any version of wolfSSL and wolfMQTT will work. But, for the sake of repeatability, I'm going to be specifying that for this particular presentation, we're using version 5.7.6 of wolfSSL and version 1.19.2 of wolfMQTT. Okay, so here are the instructions for building wolfSSL. Super simple. First of all, you download the zip archive from wolfSSL download page, which is simply wolfssl.com/download. You'll get the zip file. You'll have to unzip it and change directory into there. The configure script is already there. You'll have to define wolfSSL_no_ASN_strict, and we'll talk about that later. And then you just go ahead and configure, and you run the make, and you make install. Notably, the make install step typically requires root access. That's why the sudo is there. If you choose not to do that, you can run the configure line such that it installs in a non-root controlled area. But for now, just for simplicity's sake, we just use sudo make install. And since wolfSSL is a library, we also need to sudo ld config. Okay, so now here are the steps for building wolfMQTT. It's pretty basic, it's pretty simple. You unzip wolfMQTT's archive, and you can download it from the same page where you got wolfSSL. You change directory into the source code. You run configure and specify obviously that you're using wolfSSL. You do a make all. And then notably, you're going to need 3 files. Now, these files aren't supplied to you in this particular case because these are notably one of the files is a private key. So obviously, we're not going to be making that private key public to a wider audience. But note that we are using a standard CA certificate, which was issued by Amazon. And the reason why is because the broker is running on an Amazon server. Because the broker will want to authenticate us, we're doing, of course, mutual authentication. We're going to need the certificates and the private key to prove our identity. Notably here, we're going to be acting as the MQTT subscriber. Okay, so like I said, why are we defining wolfSSL_no ASN strict? And the simple explanation is that for some reason, the serial number within the CA certificate is 0. And generally speaking, this is frowned upon, but it happens. Some people, some certificates have serial number 0, and if you read the the X509 standard, this is generally not supposed to happen, but it does. So wolfSSL has built in the flexibility to allow this to happen. And this is no shade. We're not shaming Amazon at all. This is just something that happened. And we're basically letting everybody know and understand that we have the flexibility to handle all these kinds of cases. Okay, let's get into the demo. So the way that we're going to execute wolfMQTT is through an example. It's called the pub sub example. We're just going to use the subscriber half of the example. And the command line here is really interesting. So just to be quick, the -h specifies the host name of the broker. The -n and the -i specify the name and the topic. -q1 there specifies the quality of service level, which is 1. And -t specifies that we would like to use TLS. And in that case, we're going to need a CA certificate and our own client certificate and private key to do authentication. So -A specifies the CA cert, which is Amazon_Starfield_CA.pem. -C is going to specify our certificate that we will send over during client authentication. And -K, notably capital K, specifies the private key for us to prove our identity. And so you might be a little bit confused about the -Q1, and that's just like I said, the quality of service. And what it does is it guarantees at least one delivery. A message is stored by the sender until the receiver acknowledges it, and it's resent until acknowledgement. And in this case, the sender is the broker. I'm going to let Yanko take over from here.
Yes. So on the other side of the communication, we have the publisher. So this is the embedded device that I have running CSNet on with its MQTT client module. And it's doing pretty much the same thing that Anthony just described. It's, like I said before, it's just installing the certificate and all of that, but it's transmitting the MQTT message. In this case, it's going to be the ADC value of this potentiometer that it's on the board right now. And it's just going to continue to do that ad infinitum until it tells it to stop.
Okay, so in this demo, we're going to run the, what is this? The subscriber. As I had specified earlier, this is the command line that we're using, and I'm just going to push enter. And you can see that we can see the ADC values. Oh, and we can see Yanko's twiddling those values. Yanko,
Yes.
how are you controlling the ADC values? Is it some sort of dial?
No, just turning the knob. It's a knob.
It's a knob. Okay.
Yeah, it's a potentiometer, and it ranges from 0 to 100. And you pretty much are seeing what I'm seeing on my screen.
Excellent. And so, yeah, I'm all the way up here in Waterloo, Ontario, Canada. Yanko, you're in Weston, Florida, USA, right?
Yes.
And so this is the power of MQTT, right? You can monitor anything, anywhere in the world from anywhere in the world.
Yes, and also you can actually publish to a separate topic as well in case you wanted to have a notification that you received that message, but you wanted to have something on the back end to double verify it. So that also can be done with our MQTT client.
Excellent. And yep, I would say that concludes our demo. Okay, and I think we can safely say that yes, nothing did go wrong. So yeah, all in all, a successful demo. Wouldn't you agree, Yanko?
Oh, I would.
Good. Okay, I think we've come to the conclusion of our presentation. Shizuka, I'll throw it back to you to see if we have any questions from the audience.
Thank you. Thank you, Anthony, Janos, and Yanko. There's a question. Can wolfSSL act as a publisher as well?
Yeah, this is Anthony again. So the answer is yes. In fact, that is the main use case for wolfMQTT. Generally speaking, wolfSSL usually runs on embedded devices, and wolfMQTT is generally used in the IoT, the sensor half of the IoT part, and we can be used as a publisher. Not only that, on our roadmap, we're looking into adding a lightweight broker for MQTT as well. So we'll be a fully featured MQTT product.
Awesome. There's another question. Why didn't Weston Embedded use a wolfMQTT?
Well, there was nothing really stopping us, but I think that it was more that it was just not integrated. We just have the facility to do it with that internal task using our system. So we went with CSNet version.
Thank you. So I have another question. What's included in the Cesium RTOS 30-day evaluation?
The evaluation comes with both of our real-time kernels, CSOS2 and CSOS3. It also comes with our communication stacks, which are the network stack, the CSNet that you just saw, our USB device and host stacks, and also our FAT file system. Everything is in full source, and all the products come with the PDF documentation. And on top of that, they come with ST example projects that run on boards ranging from their L series all the way up to their newest U5 and H7 boards.
Perfect, thank you. So I have another question. Can you execute an MQTT API call within the callback function themselves?
Ooh, that's a good question. Yes, as long as you don't pend for something or wait for something or delay the task, or do something lengthy within a call stack. We usually try to dissuade people to not do anything like that. But yeah, in theory, yeah, you could, I guess, connect on a disconnect callback or publish on a publish callback. It's just gonna do it kind of as a positive feedback loop if you keep publishing within the publishing callback. But I don't think it'll cause any issues because it'll post to the MQTT task, and then it'll carry that on in a different context. So yeah, it's definitely possible.